Hello everyone, I hope you have seen my previous debut video regarding my classes, and if you have not seen yet, so I would request you all to go to my channel and watch that video. And as I told that I will upload two videos from each chapter, part 1 and part 2. Part 1 will contain the theoretical concepts and part 2 will contain the numerical. So this is the part 1 video, that is the theoretical concept from the chapter Set Theory of Class XI Concept. So please like, share and subscribe my channel as much as you can, and don't forget to press the bell notification so that you can get the notification of my every new video. And without wasting our time, we will start our today's class. So let's begin. So as our today's topic is set, and we need to know that the theory of set was introduced by the German mathematician George Cantor, and the definition is a well-defined collection of distinct objects of our thoughts or of our perception to be conceived as whole. That is, set means a well-defined collection. Now if I am giving you some examples, suppose I am taking a garland. What is a garland? It is a collection of some flowers. So I can call only one flower of that garland as the element of that collection, that is the element of that set. So a set has some elements. So usually we will represent the set always by giving the second bracket notation, and usually the capital letters, that is capital A, capital B, C, etc. are used to denote a set, and the small letters, that is small a, small b, small c, small d, these are used to denote the element of a set. So now the question is, can we call every collection as a set? That is, if we take any collection of anything, so can we call it as a set? But the answer will be no, because see, in the definition it is written a well-defined collection. Now we need to know what is the meaning of that well-defined collection. When a collection can be called as a well-defined collection. See, I am giving you some examples, then it will be clear to you. Suppose I am taking a set capital A is equals to 1, 2, 3, 4 and 5. But if I take capital B and I am taking the elements as 1, 1, 2, 3, 4, 5. So here A will be called as a set, but the collection B will not be called as a set. Why? Because see here in the B, in the collection B, the element 1 and 3 are being repeated. So well defined means there will be no repetition of elements in that collection. That is, if we get some repetition of some elements in a collection, we will not call that collection as a set. The main property that no elements of a set will be repeated. I repeat, no element of the set will be repeated. That is, in set there will be no repetition of the elements. If in a collection we see there is a repetition of the elements, so we can call that collection as a sequence, not as a set. For example, if I take, suppose C is equals to minus 1, 1, minus 1, 1, minus 1, 1 and so on. This C is a collection, but we will not call this collection as a set, but we can call this collection as a sequence, and this is oscillatory sequence we can call it. So this is the basic definition of the set. Now we need to know what is the representation of set. So here the representation of set, we can represent a set by two ways. There are two ways for representing a set. The first one is the roster or tabulation method, and the second one is the property or set builder method. Now we need to know the difference between these two methods. So suppose I am taking any example or any statement that let capital X be any set of primes less than 10. Suppose this is a statement, X be any set of primes less than 10. And now if we want to represent this language, that is the statement, by the notation of the set theory, so if we want to represent by roster method, so the another name is tabulation, that is in this method, what we'll do, we will represent each of the element individually of that set. But in the property or set builder method, we'll mention the property of that elements in that collection. So see, suppose here XB, as XB the set of all primes less than 10, so in roster method I can write X equals to 2, 3, 5 and 7. So these are the primes less than 10. So that is here we are mentioning each of the element of this collection. But if we want to represent by property or set builder method, we will not mention each of the elements. That is, what we'll write here? We'll write here X, a small x I will represent, as I told that the small elements are representing the elements of the set, that is here X, then we need to give that such that sign, that is this sign is called such that, or some author can represent it by the colon. So by giving the colon sign or that sign, we can say this is a such that sign. So we can write X such that X is prime less than 10. So this will be the representation by the property or set builder method. So students, I think it is clear to all of you that how we can represent the set by these two different ways, that is the roster method or the property method. So now we will see some definitions in this chapter. The first one is Singleton set. So Singleton set means a set which will contain only one element, not more than one element. For example, suppose let A be any set and in A there is only one element, suppose I am considering it as 5. So then A will be called as a Singleton set. Now the next one is null set or empty set or void set. That is, if there is no element in a set, then we will call it as a null set. For example, suppose let A be any set and there is no element in A, then we will call A as the null set, and the null set is represented by 5. So we will say that A is equals to 5. 5 means null set. We will not give the second bracket here. If we give the second bracket, so the meaning will be different. So then it will represent a singleton set. So we cannot give the second bracket notation after writing 5. We will write only 5. Number 3, subset. So this is a very important definition, that is a subset, and we know set means a collection, so subset means a sub-collection. That is, if we break a collection and the sub-parts we can call the subset of the main collection, that is the main set. So now how we can define any non-empty set A is said to be the subset of another non-empty set B if X belongs to A implies that X belongs to B. So now we need to know the meaning of this statement, that is x belongs to A implies that x belongs to B. Here x is any arbitrary element. If we take any element from the set A, it must belong to B. Then we can call A as the subset of B. That is, suppose this is the set capital A, then B will be larger than A. So from this picture it is clear that if we take any element from this set, and as this set is contained in B, so we can call all the elements of A will also be the elements of B. So that's why A will be the subset, and in other words we can also say that B will be the superset of A. That is, the subset will represent by that notation, that is A is a subset and will give this underline, and this means equals to B. That means A either a subset of B or A is equals to B. Here this case is improper. From this statement we cannot say anything particularly, because it means either A is a subset of B or A can be equal to B. If I write suppose x less equals to y, so this statement we can call this statement as an improper statement, because from this statement we cannot say anything particularly, because here x, either x is less than y or x is equals to y. So that's why here also we will give that underline sign and it represents the equals to. So that's why A is a subset equals to B. And in other words, if we want to say, so we will say as B is larger than A, so B is a superset of A. The same statement if we state with respect to A, then we will call it as a subset, and if we state this statement with respect to B, then we will call it as a superset. That is, suppose Ram is father of Shyam. What does it mean? That is, Shyam is the son of Ram. Same statement, both have same meaning, but we can state it with respect to Ram as well as Shyam. So here also, if we call this statement or if we state this with respect to A, we will call it A is a subset of B, and if we state this with respect to B, we will call it B is the superset of A. Now I am coming to our next definition, number 4, proper subset. So proper subset means any non-empty set A can be called as a proper subset of another non-empty set B if B contains at least one extra element than A. And we all know the difference between at least and at most. So at least means minimum and at most means maximum. So if I am saying you that give me at least 5 rupees, that means you can give me minimum 5 rupees, or if you give me more than 5 rupees, no issues. You can give also 5 rupees, 6 rupees, 7 rupees, 8 or anything else. Anything larger than 5. But if I am saying you give me at most 5 rupees. That is, you can give me maximum 5 rupees, not more than 5. So you have to give me some lesser amount than 5. That is 4, 3, 2, 1, 0, anything else. So now, here it is stated that A can be called as a proper subset of another non-empty set B if B contains at least one extra element than A. That is, in B there will be at least one extra element. So it may be more than one. That is, the number of elements in B will always be greater than the number of elements in A. So this is the definition of proper subset. That is, if we say x is less than y. Now I am not giving that equals to sign. So what does it mean? That is, here it is a proper statement. Properly we can understand that x is less than y. So here also that means we will represent this by A, only the subset. I will not give that equals to sign. So if we give the equals to sign, it will mean the general subset. So if we don't give that equals to sign, so it is the proper subset sign. So A is a proper subset of B. So from this statement, it is clear to all of us that the number of elements in A will be less than the number of elements in B. Now, something we need to know, that we know phi, this means the null set or void set or empty set. That is, in this set there is no elements. So now, we can easily say that the phi is a subset of any set. Whether you can write this proper subset. So phi is a subset of any set. Suppose A. That is any set. Obviously it will be non-empty. Now, suppose A is equals to, I am saying 1, 2, 3. So I can say A is a subset equals to A. So that means A is equals to A. This condition is being satisfied. So every set, we can call it that every set is a subset of itself. So these two things we need to keep in our mind, that the null set is a subset of every set, and as well as the every set will be the subset of itself. Now I am coming to our next definition, cardinality of sets. So the cardinality means the number of elements contained in the set. That is, the total number of elements which will be contained in that set. Suppose A be any non-empty set and I am taking A as 1, 2, 3. So I can say the cardinality of A is 3 and we will represent this n of A. That is number of elements in A, that is equals to 3. So now we are coming to our next definition, that is equality of two sets. So equality of two sets means if A and B be any two non-empty sets, then A and B are said to be equal if A is a subset equals to B and B is a subset equals to A simultaneously. That means, if I am saying, suppose x is less equals to y and also y is less equals to x. So here x is less equals to y, that means either x is less than y or x is equals to y. Same here, y is less equals to x means either y is less than x or y equals to x. So if x is less than y, so how y can be smaller than x? So that contradicts. So we have to take the common condition, and the common condition between them is equals to. So we will write here x is equals to y. So same thing we will apply here. So a is a subset equals to b and b is a subset equals to a. If we take this condition, a is a subset of b, then how b can be a subset of a? B should be the superset of a. But both the conditions hold simultaneously, so we have to take the common condition between them, and the common condition is equals to. So we'll write a is equals to b. So this is the equality of two sets, but there is also equal sets. An equal set is different. Equal set means if both the set have same element, then we can call the sets as equal sets. For example, suppose I am taking equal sets. So suppose let a is equals to 1, 2, 3 and b is equals to 2, 3, 1. So here both the sets a and b have same elements. So as they have same elements, so we can call a is equals to b. This is not equality. Equality means the condition for being equal. But equal set means which have same elements. If a and b, you can see from that example, here a and b have same elements, so I am calling it as equal sets. But equality means the condition for being equal. So that's why this is the condition, that is a will be a subset equals to b as well as b will be a subset equals to a. So don't get confused between these two things, equal sets and equality of two sets. Now I am coming to our next definition, power set. Power set means power set is a set and which will be constructed by all possible subsets of any set. That is, suppose I am taking any set A as 1, 2 and 3. So now the number of possible subsets that can be constructed by the elements of A. If we want to construct, that is, we can construct the Singleton set 1 as well as 2 as well as 3, and if we take the pair of elements, so 1, 2, also we can call it a subset, 2, 3, 3, 1, and from the previous I have told already that the null set is a subset of every set. So 5 is a subset of A also, and also I can say every set is a subset of itself. So A, and that means this means 1, 2, 3 is also a subset of that set. So with these sets, if we consider these sets as the elements, and if we take a big set of sets, so that will be called the power set of A. That is, it will be represented by P of A. That is power set of A. So here you have to keep in mind one thing, that if a set contains n elements, then its power set will contain 2 to the power n elements. That is, from here you can say directly that suppose cardinality of any set is 4. I am taking any set A whose cardinality is 4, that is the number of elements in that set is 4. That is, A contains 4 elements, so then its power set P of A will contain 2 to the power 4, that is 16 elements. So we can make 16 possible subsets of that set A. And you can see also from the previous example here, A contains 1, 2, 3, 3 elements. So in its power set, it should contain 2 to the power 3, that 8 elements. So count 1, 2, 3, 4, 5, 6, 7 and 8. So 8 elements. And moreover, one thing you need to know that phi and A, these are the subset we know that every set. And these subsets are called improper subsets. It is obvious. This case is obvious, that is vacuously satisfied. This is. So every set we know, as in phi there are no element. So phi will always be a subset of A, as well as every set you know that every set will also be a subset of itself. So as these two conditions are obvious conditions, so we will call these two sets, that is the two subsets, as improper subset of any set. And other than these two subsets are called proper. So here 6 subsets are proper and 2 subsets are improper. Now we'll see some algebraic operations on sets. So there are 5 types of algebraic operations we can apply on set. So the first operation is union. If A and B be any two non-empty sets, then the union of these two sets will be represented by A, U, B, and here U stands for the union. And union, what does it mean? Union means we are adding these two sets. That is, we are collecting all the elements, or we are combining all the elements of these two sets. That is, so if we want to represent it by the set builder way, so we can write X such that X belongs to A or X belongs to B. So this sign is called belongs to, and this sign is called or. So you can represent by the sign or by the words, whatever you like. Now I am giving some example. Before that, I am showing you the Venn diagram, how it will look like. So if this is A and this is B, so as we are combining the elements of these two sets, so the common region will be the whole part. And these types of diagrams are called Venn diagram, and it was named by John Venn, a mathematician. So by these Venn diagrams also we can represent the operations on set instead of representing them algebraically. So now if I am giving you some examples, so first let A equals to 1, 2, 3 and B equals to 4, 5. So if we take the union of these two sets, so A union B will be 1, 2, 3, 4, 5. And example number 2, suppose I am giving you A equals to 1, 2, 3, 4, 5 and B equals to 4, 5, 6, 7. So if we are combining these two sets, so we will write A union B equals to 1, 2, 3, 4, 5, 6, 7. We will not write the elements twice. So see, here some elements are common between A and B. Here 4, 5 in A, there are two elements 4, 5 also in B. So we will not write twice, because you know the definition of set, that should be a well-defined collection. So no repetitions of elements will be allowed in set. So that's why I will write only one time. So number of repetitions of 4, 5 will be only 1, not more than 1. So now we are coming to the next operation, intersection. But before that, you need to keep in your mind from this operation that for union we will always get the or. That is, if we break the union, we will get or, and if we want to ignore or, so we have to take the union. That is vice versa. So union means addition, and for breaking this we will get or. So union means always or. Now I am coming to the second operation, that is intersection. So let A and B be any two non-empty sets, then the intersection of A and B will be represented by A intersection B. So the sign of intersection is this, that is, if we reverse the sign of union 180 degree vertically, so we'll get that sign. So now, and if we want to represent it by the Venn diagram or algebraically means that by the set builder way, so we will write A intersection B equals to X such that X belongs to A and X belongs to B. So this is the notation for and you know this is the sign for belongs to and this is and. That is, intersection means the common region. That is, if we do the Venn diagram, this is A and this is B. So the common region between A and B, that is the overlapped area, and the overlapped area is this. So this shaded region will be the intersection. So intersection means the common chord, and if we break the intersection, we will get an and sign, and vice versa. If we ignore the and sign, we have to take the intersection. So now if we see some examples, let A equals to 1, 2, 3 and B equals to 3, 4, 5. So A intersection B, it will be only 3 is common between the two sets. So we will write 3. That is, the intersection B will be the Singleton set. Now let's see the second example. Suppose A equals to 1, 2 and B equals to 3, 4. So there are no common elements between A and B. So A intersection B will be equals to 5. That is the null set. We will not give the second bracket, because as I told, if you give the second bracket, so this will represent a singleton set. That is, 5 will be considered then one element. So we will not give this second bracket. We will write only 5. That is, for representing the null set, we will write only 5. And now we are coming to our third operation, that is complement or complementation. So from the junior classes we know the complementary angle and supplementary angle. So complementary angle means if the sum of two angles is 90 degree, and supplementary was if the sum of two angles are 180 degree. So suppose I am asking you what will be the complementary angle of 40 degree. So you will say that 90 minus 40, that will be 50 degree. So that is, for finding the complementary angle of any angle, we need to subtract that angle from the 90 degree. So here also the same concept will be applied. So see how we can find the complement of any set. So if A be any set, then the complement of A will be denoted by A bar or A dash you can give, or A and at the top you can write a C. C stands for the complement. So and A complement means that, suppose consider A as the example 40 degree, and what you have done, that 90 minus 40. So here also we are interested for finding the complement of A, so we have to subtract A from a universal set. So we will write U minus A. So consider this universal set as 90 degree and A as 40 degrees. So the A complement will be 90 minus 40. So same thing. In normal mathematics, what we are doing, that is the normal algebra, what we will do, we will also do just like that in the set algebra. But there are some differences between the normal algebra and the set algebra. So now, so if we want to represent this by a Venn diagram, so this is the universal set. Universal set means our mother set. That is the mother of all sets. And every set will be considered as the daughter set of that universal set. So here, let U be the universal set, and by this quadrilateral I am representing that universal set, and this is the set A. So A complement means U minus A, that is, from this universal set we will subtract this A. So what will be left? This outer part. So this will be the complement of A, that is A, C or A bar, what you can say, that depends on you. So now if we want to represent this by the set builder way, so we will write X such that, see, if we take any element from this shaded region, it will mean that it will belong to the universal set, but it will not belong to A. So we will write X belongs to U and X does not belong to A. So A complement means the outer portion of A. That is, if we take any element from the A complement, that means that element will not belong to that set. So this is the A complement, and if I show you some example, let U equals to the whole number and A equals to the set of all natural numbers. So if we find A complement, that is U minus A, and U means whole number minus A means natural number. So whole number minus natural number, and we know that whole number starts from 0 to infinity, but the natural number will start from 1 to infinity. So if you do the singleton set, 0. If we subtract this, we will get only 0. So this is the complement. Now we are coming to our next operation, and before that, one more thing, that suppose we are finding A union A complement. So what we get? That if we take the union of any set and its complement, so see, this is A and the outer side is A complement. So if we take the union, that is, if we combine or if we add these two sets, we will get the universal set. And similarly, if we take A intersection A complement, so this is A and the outer side is A complement. So there is no common region between these two sets. So we will get nothing. That is, we will write a part null set. Now we are coming to our next operation, that is difference. So if A and B be any two non-empty sets, so the difference of A and B will be represented by A minus B. And this is the sign for difference. You all know that for difference means the subtraction we will do. So here A minus B, that is the difference. And if you want to represent this by set algebra, so we will write X such that A minus B, that is, we are subtracting B from A totally. So every element that will belongs to A but will not belongs to B. Why? Because we have subtracted B. So that means X such that X belongs to A, and since B is being subtracted here, so we'll write X belongs to A and X does not belong to B. That means we can easily say X belongs to A and X does not belongs to B. That means we have seen X does not belong to B means X belongs to B complement. And already I have told you that if we want to ignore the AND sign, so we have to take the intersection, because union means OR and intersection means AND. So here we will write X belongs to A, we are ignoring that sign, so we have to take the intersection of these two sets A and B complement. So A intersection B complement. That means A minus B, A intersection B complement. Similarly, if we write B minus A, it will be B intersection A complement. Similarly, if we write C minus D, it will be C intersection D complement, and so on. So the first set will be as it is, then we have to give the intersection sign and we have to take the complement of the second set. So now if we see the Venn diagram of the difference of two sets, so suppose this is A and this is B. So A minus B, that means we are subtracting B from A. So this part, that is the B, will be removed from that. So what part will left? This region. So this is A minus B. So similarly this part, if we want to say the name of this part, the dotted region, so it will be B minus A, that is here A is being subtracted from B. Now I am giving you some example. If A equals to 1, 2, 3 and up to 10 and B equals to suppose 3, 4 up to 10, so A minus B, it will be only 1 and 2. That is from the first 10 natural numbers we are subtracting the natural numbers from 3 to 10. So what will be there? That is only 1 and 2. So this is the difference, and also one thing you need to keep in your mind, that A minus B and B minus A, that are not equal in general. We can't say anything about these two sets, A minus B and B minus A. The operation number 5, that is symmetric difference. So if A and B be any two sets, the symmetric difference of A and B will be represented by A delta B. And if you want to represent this by a Venn diagram, so this is A and this is B, and this will be the region A delta B. That is, as the difference is symmetric. Symmetric means if we rotate this by 180 degree, so it will look same. So see here, if we exchange this part, so both sides will look like same. So the figure will look like same. So that's why this difference is called symmetric difference. So this naming I can call it as, so this part is A minus B, and this part B minus A. So you can write the formula for symmetric difference as A minus B, and if you union these two sets, union B minus A, will get the symmetric difference, as well as we can also write A union B, that is from the whole part. If we subtract this dotted part, so also we will get that symmetric difference. So that is minus A intersection B. So this is the symmetric difference. So now we will see some algebraic laws on set. So the first law, that is A union A is equals to A, and also A intersection A is A, and this law is called idempotent law. Every law of the set theory has two versions. One will be the union version and the another will be the intersection version. So the union version, that is, it is very obvious law that A union A is equals to A and A intersection A equals to A. Suppose if A equals to 2, 3 and 4, so if we take A union A, so we will not write 2, 2, 3, 3, 4, 4. We will only write 2, 3 and 4, because as you know, in a set no elements will be repeated. So you will get A only. So similarly for intersection we can say that same thing. So that's why this law is called idempotent law, the name of this law. Now we are coming to a second law. That is A union B union C equals to A union B union C, and this is the union version, and the same thing will be in the intersection version. That is A intersection B intersection C, we can write A intersection B intersection C. So this law is called associative law. So here, why it is called associative? Because we are doing the association of the union and intersection signs. That is A union B union C. We are just rearranging the terms. That is, we are associating the terms A union B. We are taking this in one bracket and then C. So that's why this law is called associative law. In everyday context, that is in normal algebra also we are using that law. So see, we can write 2 plus 3 plus 5. We can write also 2 plus 3 plus 5. So here also we are associating. And union, you know, union means that is addition, and intersection means multiplication. Always keep in your mind. So that's why 2 plus 3 plus 5, we can write it 2 plus 3 and plus 5. So this is the associative law. So also we can write 2 into 3 into 5 is equals to 2 into 3 into 5. Here also we are applying the associative law. But the name was unknown to us. Now we are knowing the name as the associative law. No change we are doing from the normal algebra and the set algebra. Now we are coming to our next law. Law number 3, that is A union B intersection C equals to A union B, and the intersection will come out then A union C. Similarly, for the intersection sign A intersection B union C, we can apply this law as A intersection B, then union will come out, and A intersection C. Here what is going on? That is, here see the first statement, the union sign, it is being distributed over the intersection sign. That is, A union B I am doing, and here also I am doing A union C. That is, here union is being distributed over intersection, and the second part, intersection is being distributed over union. So this name is distributive law. In normal algebra also we are often using that laws. That is, this is the distributive law, and if I write suppose 2 into 3 plus 5, so I can write it as 2 into 3 plus 2 into 5. So here that multiplication sign is being distributed over addition, and as I told, union means addition and intersection means multiplication. So if we convert this, that is 2 means if we write as A, and multiplication means intersection, and 3 means B, and here if we write addition, that is union, and this is 5, so 5 means C, so we can say that A intersection B union A intersection C. So we can get that law. So now we are coming to our next law, that is law number 4. A union B equals to B union A, and similarly A intersection B equals to B intersection A. So this law is called commutative law. So here what is going on, that is the two sets A and B, we are interchanging their positions over union and as well as intersection. So that's why this law is called commutative law. That is, if we take the union of A and B, and again if we take the union of B and A, we can get the same answer. So it is very obvious, that is, if we take A as 1 and 2 and B as 2 and 3, so A union B we will get as 1, 2, 3. So similarly, if we find B union A, we will also get B means 2, 3 and also 1. So the same elements we are getting, so that's why these two sets will be equal. Similarly, for intersection we can also prove that same thing. Now we are coming to our next law, that is De Morgan's law. So this is the most important law in this chapter, that is set theory, and this law is often being used in solving the numericals of this chapter. So we need to clear the concept of this law. And this law states that A union B, and if we take the complement of the whole set A union B, so it will be A complement, the union will be interchanged to intersection and B complement. Similarly, for the intersection version we can write that is A intersection B and its complement, it will be A complement union B complement. And the last law, that is absorption law. So absorption law means A union A intersection B will get as A. Similarly, A intersection A union B, if we find, we will also get A. If we draw the Venn diagram, so this law will be clear to us. If this is A and this is B, and A intersection B means this overlapped part, and we are taking the union of A and A intersection B. So A means the whole set and A intersection B means the smaller part. So if we take the union of a larger part and a smaller part, so we will obviously get the larger part. So it will be A. So that's why I have written this as A. And similarly A union B. A union B means this whole set, and we are taking the intersection of this A and A union B. A means only this region, that is this is the smaller part and the whole set is A union B. So and if we take the intersection of a larger part and a smaller part, we will always get that smaller part, because intersection means the only the overlapped portion. So it will be always the smaller part, so that's why it will come as A. So I have written the result is as A. In this law, B is being absorbed by A. So as B is being absorbed by A, so the name of this law is absorption law. Now we are coming to our last law, that is addition law. So what is addition law? We need to know first. So if this is A and this is B, so we know that portion is called A minus B, and this portion is called B minus A, and this dotted portion is called A intersection B. So now see, as this whole part is A union B, so we can write A union B equals to A minus B plus this is A intersection B plus this is B minus A. That is, if we take the addition of these three portions individually, we will get the whole portion. That is, the whole portion is A union B. So I can write the cardinality of A union B, that is the number of elements in A union B, equals to the number of elements in A minus B plus number of elements in A intersection B plus number of elements in B minus A. And I am taking this equation as number 1. And now again we can say this whole portion is A, we know. So as this whole portion is A, so I can write A is equals to, A means this portion, this is A minus B, and that portion, that is A intersection B. So I can write A as A minus B plus A intersection B. So we can say number of elements in A is equals to number of elements in A minus B plus number of elements in A intersection B. Similarly also, as this whole set is B, so I can write B as B is equals to, this portion is B minus A, that is B minus A plus, and this portion is A intersection B. So we can write number of elements in B is equals to number of elements in B minus A plus number of elements in A intersection B. So I am making this equation as 2 and this equation as 3. So we can also say from 2, that is n of A minus B, that is n of A, and if we take this n of A intersection B to the other side, so it will be minus A intersection B. Similarly by 3, we can say n of B minus A is equals to NB minus n of A intersection B. So now if we substitute these two values in this equation, so what we'll get, that is n of A union B equals to n of A minus B, and n of A minus B means NA minus n of A intersection B plus, this is n of A intersection B plus n of B minus A, and n of B minus A means NB minus n of A intersection B. So now this plus n of A intersection B and minus n of A intersection B will be cancelled. So what we will get, n of A union B equals to NA plus NB minus n of A intersection B. So this is the most important law, because the word problems in this chapter will be done by using that law. So we need to know that law, and if we go through the proof, that is the mechanism of the law, so we'll get these two laws also, and these two laws will also be applied for solving the numericals. That is, for two sets we are getting that n of A union B equals to NA plus NB minus n of A intersection B. So similarly we can make this law for the three sets, and if we make, we will get n of A union B union C equals to NA plus NB plus NC minus n of A intersection B minus n of B intersection C minus n of C intersection A plus n of A intersection B intersection C. So why we are getting that so large term? Because in the previous part we had only two sets, A and B. So that's why we had written that NA plus NB minus n of A intersection B. But now we have three sets, so according to the similar way we will make that for the three sets we will write first NA plus NB plus NC. Then in the previous part the only one possible pair, it was A and B, so n of A intersection B. Now there will be similarly, as we are making this, so we will get three possible pairs, so we are subtracting minus n of A intersection B minus n of B intersection C minus n of C intersection A. then plus n of A intersection B intersection C. So everyone, so these are the concepts that we should know before going to the numerical section. So students, I am ending my today's class here, and we'll meet on our next class with a new video that will contain the numerical of this set theory chapter. And once more I am telling you, who have not subscribed my channel still now, so please like, share and subscribe my channel, and don't forget to press the bell notification. And with respect to the present scenario, please stay home and stay safe. Goodbye, take care.